Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics, lecture number 20. Before starting this lecture, let's see what we have done in the last lecture. We started with the topic Laplace transformation, and we went on to define this transform and then find out the Laplace transform of some elementary functions. Then we went on to study the properties of this transform and also implemented those properties on different examples. Today we will continue with the Laplace transform, but we will study the inverse Laplace transform. That if you are going from ft to fs, then can you come back or not? Right? So if you have taken the Laplace transform of some function and got the new function, can you do something with the new function to get your original function back? All right. If there is a transform, that is called inverse Laplace transform. Then we will study the properties of inverse Laplace transform, and then we will go on to implement this Laplace transform to integral equations. All right. Volterra integral equation using Laplace transform method and solution of Integro-differential equation using Laplace transform method. Integro-differential equation was when there are both the terms differential and integral terms appearing in your equation. All right. So by defining Laplace transform and inverse Laplace transform, we can implement them to integral equations as well. So today we will see both things. So let's start with the inverse Laplace transform. What the inverse Laplace transform is. Inverse Laplace transform, in the previous lecture we have discussed various properties of Laplace transformation and obtained the Laplace transform of some simple functions. However, if the Laplace transform technique is to be useful in applications, we have to consider the reverse problem too. That is, we have to find the original function ft when we know its Laplace transform capital F. Let's say if capital F of s is given to you, that someone says that this is the Laplace transform of some function, find out that function, then you should implement the inverse Laplace transform technique to get your original function back. This is the same as differentiation and integration. When you differentiate some function, you get another function. If you integrate that function, you get your original function back. Right? So it's the same thing. Can you get your original function back or not? So if the Laplace transformation of ft is capital Fs, that is, this is not x, this is of course s, that is L of ft is equal to capital Fs, then ft is equal to Laplace inverse of capital Fs. Right? L goes on the other side and becomes Laplace inverse. It's the same as in the case of any operator. It can be differential operator, sine, cosine. When you send that to the other side, it becomes the inverse, if inverse exists. This is the question. So let's try to find out the Laplace inverse transform of some function. We have seen some functions and Laplace transform of those functions. So maybe recalling those formulas, let's say if we are able to find out the inverse Laplace transform of naught. Now if you recall, 1 over s was the Laplace transform of 1. So it means Laplace inverse of 1 over s should be equal to 1. Simple as that. What was this function Laplace transform of? Do you remember? 1 over s minus a was the Laplace transform of e to the at, right? So it means the inverse Laplace transform of this function is e to the plus at. And this is e to the negative at. This is t to the power n. This is cosine at. This is sine at. And this is, remember? Here is the problem. I didn't see any function like that, right? When we were doing the Laplace transformation in last lecture, till these all functions are okay, but we didn't see a function whose Laplace transform came out to be like this. But I guess it is s square plus a square square, so it looks like it is the derivative of this thing, right? derivative of something like this, a over s square plus a square. This is the transform of sine hyperbolic. But if you take the Laplace of sine, it is a over s square plus a square. If you take the derivative of a over s plus a square, it is exactly this one. All right. So we know that when we take the derivative, we have to multiply by t. So this will be a good idea to solve, find the Laplace transform of this last function. So you are looking for Laplace transform of 2as divided by s square plus a square square, and it will go to t, of course, right? This is what we need. What I remember is the Laplace transform of sine at with s was a over s square plus a square. But my answer is the derivative with respect to s of a over s square plus a square. And this derivative is s square plus a square square, and the derivative of s square by a square is 2s, so this is 2as. So now we have exact same thing. So this can be written as the derivative of this one, and you know that if it is first derivative, then it should have minus 1 to the power 1 with it. All right, so it means I'm getting negative with it, not just 2as. So, and if you remember, this is obtained by multiplying 1 power of t. Right? If we multiply 1 power of t, it gets differentiated. The answer gets differentiated. But this minus sign will give me minus sign here as well. So it means that Laplace inverse of this right hand side minus 2as over s square plus a square whole square t is nothing but t sine a t. And this minus is compensated with this minus, and this minus is gone. All right. So this is what I got. After some manipulation, I got the Laplace inverse of this thing. Just by observing that this is the derivative of some well-known. This is the derivative of some well-known transform. All right. So we use that property of Laplace transform to get this one. All right. So sometimes you may see that the function is difficult and we don't know what that transform should be, but by using the properties of Laplace transform, we can cope with these type of functions as well. All right. So now there is a remark that the inverse transform may not be unique. You may not get the unique only one inverse transform of some function. So for example, if we have two functions ft and gt such that ft is 1, gt is 1 for just t goes from 0 to 3, and at t is equal to 3 it is negative 8, and if t is positive greater than 3 it is again 1. All right. The Laplace transform of both the functions is 1 over s. If you try and see, the Laplace transform of both functions is 1 over s. Therefore 1 over s has two inverse transformations. However, only continuous function with transform 1 over s is 1. So if you this is discontinuous function, you can clearly see that at t is equal to 3 it has a discontinuity because it has a jump. It was at 1, all of a sudden it went to minus 8, and again it came back to 1. So of course at t is equal to 3 it has a discontinuity, but if you are looking for a continuous inverse transform, that is only 1, which is fx is equal to 1. But if you don't impose the condition of continuity, then I have two functions, all right, which are both the inverse Laplace transforms of 1 over s. So in this way, your inverse transform may not be unique. All right. What are the properties now? Properties of inverse Laplace transform. First, shifting property. You know that when your function, original function was multiplied by e to the at, your answer was shifted to s plus a. Now if you are taking the Laplace inverse of s plus a, you can take the Laplace inverse of just s, all right, and multiply by e to the negative at. And there is a change of scale property. This is see s plus a, the translation, and this is alpha s, which is scaling. That if you multiply s by a constant, then what will happen? Then your transform gets multiplied by the inverse of a, 1 over a, and t is also replaced by t by alpha. All right. So if you scale your s by alpha, your t is scaled by 1 over alpha, and your original function is also scaled by 1 over alpha. All right. So these are two very nice properties of Laplace inverse transform. Let's see how to find the Laplace inverse transform of this function. It looks like very complicated function, right? But let's try. It looks very complicated function, but let's try. We should be able to do that. Okay. All right, so this is the example. We need to find the Laplace inverse transform of this complicated function. First of all, of course, I cannot write it directly. So one thing is for sure, that if s plus 1 is separate and s square minus 2s plus 2 is separate, then we may be able to do something. And do you know the technique? If you remember the technique, how we separate the factors in the denominator? By using partial fractions, right? We have done it in integration many times. So using partial fractions, I can write, we can write 4s square minus 3s plus 5 over s plus 1 s square minus 2s plus 2 is equal to a over linear factor and bs plus c over quadratic factor. All right? And then we multiply by this whole denominator. You get 4s square minus 3s plus 5 is equal to a will get multiplied by s square minus 2s plus 2, and bs plus c will get multiplied by s plus 1, s plus 1. So first of all, if we set this s plus 1 equal to 0, means s is equal to negative 1, that will give me 4 plus 3 plus 5 equal to a times 1 plus 2 plus 2 plus b0 plus c0, because s plus 1 is 0, so these both terms will drop out, and from here I'll get the value of a, which is 12 by 5. Now, because there are no more linear terms, I cannot assume other values, so what I can do is I can compare the coefficients on both sides. So if you compare the coefficients of s square, I'll get 4 is equal to a plus b. So from there I will get b, right? And similarly, you can compare the coefficients of other terms as well. So comparing coefficients of s square and s, why just 2? Why I cannot compare other? Because I am left with only 2 more coefficients. So I need just 2 equations. One is done. I need b and c. So for b and c, I need just 2 equations. So I can compare either s and constant, or s square and s, or s square and constant. Any 2 equations who involve b and c both. All right. So you got 4 is equal to, so s square gives you 4 equal to a plus b. If you see here, s square has 4 as coefficient, here a and b both are coefficients of s square. So this implies that b is 4 minus a, right? B is 4 minus a. So 4 minus 12 by 5, which is 8 by 5. All right. And if I compare the coefficients of S, I will get minus 3 equal to minus 2a plus b plus c. Minus 2a plus b plus c. So from here your c is equal to minus 3 plus 2a minus b. So that is negative 3 plus 2a means 24 by 5 and minus b means 8 by 5. So that is minus 15 plus 24 minus 8 over 5. So that is 15 plus 8 is 23. So that is plus 1 by 5, sorry. All right. So your B is 8 by 5 and C is 1 by 5. So now I got all the coefficients, and A, let me write A as well. So this is your B, this is your C, all right. This is your B, this is C, and A is 12 by 5. So A is 12 by 5, so that is the summary. So you got all the coefficients calculated. So therefore, your given expression 4s square minus 3s plus 5 over s plus 1 s square minus 2s plus 2. This becomes a over s plus 1, so it becomes 12 by 5 over s plus 1, and plus b over b is 8 by 5 times s plus c is 1 by 5 over s square minus 2s plus 2. All right. So now I need to take the Laplace inverse, but this is fine. I know the Laplace inverse of s plus 1, but here we still have problems. So what we need to do is we need to complete the square here. If you complete the square, it is s minus 1 square plus 1. Because this is s square minus minus 2s plus 1, and I'm left with another 1 because I have 2, I don't have 1, so I will write plus 1. So plus 1 means plus 1 square. All right. So I got 12 by 5, 1 over s plus 1 plus 8 by 5 s over s minus 1 square plus 1 square, and then plus 1 over 5, 1 over s minus 1 square plus 1 square. Now you see 1 is cosine and 1 is sine, because you have s minus 1 square plus 1 is sine, this is cosine. But if you have s minus 1, you should have s minus 1 here as well. All right. So that minus 1 will be compensated, because minus 1 means you are subtracting 8, negative 8. So negative 8 will be compensated with this 1. All right. So you will be adding 8 here. Then they will be equal. All right. Then they will be equal because you subtracted negative 8 here. So you have to add 8 by 5 and the same expression. So now you can find the Laplace inverse easily. So therefore, Laplace inverse of our function with t, this function, all right, is equal to, because Laplace is linear transformation, so it is equal to 12 by 5 Laplace of 1 over s plus 1 plus 8 by 5 Laplace inverse of s minus 1 over s minus 1 square plus 1, and then plus 9 by 5 Laplace inverse of 1 over s minus 1 square plus 1 square. Now recall 1 over s plus 1 is the Laplace transform of e to the minus at. So you got 12 by 5 e to the minus t. A is 1. A is 1, so it's e to the negative t. Here, this is the Laplace transform of cosine t, cosine 1t, but s is shifted to s minus 1. So you remember when it got shifted. When it got shifted, it means it was not just cosine, but e to the power t was also being multiplied. That's why it got shifted to s minus 1. All right. So this is plus 8 by 5, not just cosine 1t, rather e to the t is also being multiplied. That will shift. Cosine t has Laplace inverse s over s plus 1, right? But we know that s is being replaced by s minus 1. It means we shifted the origin to s minus 1, and this happened only when your original function gets multiplied by e to the t. Same thing happened. This is sine st. Sine t gets multiplied by exponential. Plus 9 by 5 e to the t and sine t. So that's the Laplace inverse which we are looking for. All right, so that's your inverse. And if you want, you can further simplify. It's your choice. But if you leave it here, it's fine. Et is common, 5 is common, so you can write 8 cosine t plus 9 sine t. It's not necessary, of course. It's your choice how you want your answer to look like. All right, so that's the so see, sometimes to get the inverse transform, the point here is basically sometimes when you need to calculate the inverse Laplace transform, it will not get directly from the properties. Right? Sometimes you have to manipulate the functions, write it into the standard forms. All right, so we basically divided our whole function into 3 different types of functions whose inverse transforms were known. And then we use the properties, shifting properties and stuff like that. All right, so we found the Laplace transform of this function. Similarly, you can obtain the Laplace transform of other functions as well. Here, because it's 1 over s plus a to the power n, so derivatives will be used because we know the Laplace transform of 1 over s plus a. All right, so here what we can do is we can either use the shifting property with Tn, because Tn has Laplace transform as n factorial over Sn plus 1. So Tn minus 1 will have this Sn and then shift the origin. Or you can take 1 over s plus a, which is the inverse transform of e to the minus at, and then differentiate it n times. Again, t to the n will come on your original function. So similarly here you can use partial fractions again. Here you can simplify if you want. First, log means it is coming with the integral, right? So again, you can use the properties of derivatives and integrations to get this Laplace transform. So try them; they will not be difficult. All right. Next is the definition of the Heaviside function. You know what the Heaviside function is, of course. The unit step function or Heaviside function is defined as h t minus a. It is 0 before a, it is 1 after a. All right, when t is less than a, it is 0. When t is greater than a, it is 1. So it is a unit step function. It is 0 before a. So once it reached a, it jumps at 1 and start going like this. So it's a unit step function. That's it. It takes step of 1 unit at t is equal to a. So if you want to find the Laplace transform of this unit step function, what we need to do is we just need to multiply Heaviside function with the e to the minus st and integrate. And now we know that because this Heaviside function is defined piecewise for less than and greater than values of a, so you can break your integration from 0 to a and from a to infinity. So from 0 to a, your Heaviside function is 0, and from a to infinity, it is 1. So basically, you need to integrate from a to infinity only, and this is plus inside. Of course, it's plus, not just dt. E to the minus st divided by s. And now you can integrate from 0 to infinity, you will get e to the minus as by s. So Dirac delta function has Laplace transform of e to the negative as only. But Heaviside function has the e to the negative as divided by s. So Heaviside function has this 1 over s factor additionally, which Dirac delta function did not have. So it means when you are multiplying your, when you are getting exponential in your answer, so either Dirac delta function or Heaviside function will be coming in your original function. We studied first shifting property of inverse Laplace transform, which was coming from e to the at multiplied by the original function. All right. Here what is happening? What if your inverse Laplace transform already have e to the minus as? Then what will you do? Then we will use this Heaviside function. This Heaviside function to get rid of that. So if your original Laplace transform will be multiplied by e to the minus as, then the Laplace inverse is this, that of course fs has Laplace inverse transform ft, so you will shift your origin from t to t minus a, all right, but Heaviside function will be multiplied. It means for t greater than a, you will get this function. For t less than a, it will be 0. All right, Heaviside function means that if t is greater than a, it is 1, so you will be getting the function. But if t is less than a, it is 0, so you are not getting anything. You are getting 0 for t less than a. All right? So this is the second shifting property. Here, it's very easy. What is your capital Fs? It is s square plus 1 only. What is the Laplace inverse of s 1 over s square plus 1? It is sine t. Sine t. But because e to the minus as is multiplied, so I will change my t from t to t minus a. So it will become sine of t minus a. But when you do that, you multiply the Heaviside function as well. So answer of this example is sine t minus a times h of t minus a, means multiplied by the Heaviside function. It's very easy to use this property for this example. Now, we haven't seen the product yet. Addition is fine. Multiplication by tn or e to the at is fine. Multiplication in inverse Laplace transform as well. Multiplication with e to the minus at is fine. But we did not see two general functions getting multiplied. Let's say I know the inverse transform of one function. I know the inverse transform of the another function. They are getting multiplied. Can we find the inverse Laplace transform for that? The answer is yes, and the answer is convolution. All right. So we define convolution. If f and g are the Laplace transform of small f and small g respectively, then fg is the Laplace transform of this thing. Means the product is the Laplace transform of this thing, and this is defined as the convolution basically. All right. That is, the Laplace inverse of fs and gs is ft star gt. Ft star is the convolution basically. And this convolution is not defined by just the product. It's defined by f of one is t minus u and the other is u. All right? You can have fu and gt minus u. It's not a problem. You can keep one, like if you want to keep first one at u, then second will be t minus u. If you want to keep second as u, then first will be t minus u, and integration from 0 to t. So this is the convolution of two functions. This integral is called convolution of f and g and denoted by star. Also, f star g and g star f are the same. That's why we said these two integrals are the same. All right? Find the inverse Laplace transform of this. S over s square plus a square square. We did it once before, this type of Laplace transform, by taking the derivative. We know that s over s square plus a square is the derivative of s over s square plus a square. If you take the derivative, you will get 2as over s square plus a square square. But 2a can be adjusted. It's a constant. So we had that one way of finding the Laplace inverse. But another way is that you can write this as a product of this thing, s over s square plus a square and 1 over s square plus a square. But with s square plus a square, we need a at the top. So I replaced 1 by a and divided by a on the outside. All right. Now we know that the Laplace inverse of this thing is cosine and Laplace inverse of this is sine. So I know these two functions are the Laplace inverse of cos and sine. So it means this product will be equal to the convolution of cos and sine. So your answer will be equal to the convolution of sine and cosine. Cosine t minus u and sine u. You can use integration by parts easily and obtain the answer. Not a problem at all. All right? So if you integrate this right hand side, you will get this. T sine a t by 2a. And if you recall, we did it before. We did it before with 2as. If 2as answer was t sine at, that's it. As I said, you can adjust 1 over 2a with 1 over 2a and see 1 over 2a is coming with it. All right. So that was one way of doing it, but here we use the convolution because it's a product of two inverse transforms. Sorry, it's a product of two transforms. So inverse transforms can be obtained by the convolution integral. All right. So let's implement this in Laplace transform technique to solve integral equations now, because I know how to handle now integrals and derivatives and stuff like that. So let's implement it. Just defining Laplace transform and getting the Laplace transform of some basic variables, and then defining the inverse Laplace transform and obtaining the inverse Laplace transform of some functions is not enough. Why we are doing it? Why we are defining a new transform and getting our life more difficult? Why we are doing it? Of course, we need to use it somewhere. So one of the application is solutions of differential and integral equations using the Laplace inverse technique. All right. So now we will be implementing this technique to solve Volterra integral equation. All right. So again, a kernel kxt is called a difference kernel if it is dependent on difference of arguments. Right? If kxt is k of x minus t, let's say, it's a difference kernel. Remember when we started integral equations and we defined kernels, and then we defined some special kinds of kernels? This was one of them. If you go back to that lecture and see, the difference kernel is one of them. So it is just the difference of x and t inside. Like whenever you see a function, whenever you see xt coming, they will be coming together in the form of x minus t. All right. The Volterra equation of the second kind with difference kernel can be written as this. Ux is equal to fx plus 0 to x. Now my kernel is not x comma t. It's a difference kernel, so I can write it x minus t, ut dt. And you are very much familiar with this Volterra integral equation. We have spent handsome amount of time solving Volterra integral equations. Taking Laplace transform of both sides, we obtain, if I take just the Laplace transform of both sides, all right, we obtain L ux, L fx, lambda L, and this whole thing. This becomes u bar. U bar, I'm using Laplace transform. One notation we used was f goes to capital F. You can do it here as well. U goes to capital U. This is another notation. Sometimes they write u bar as the Laplace transform of u. So this is just the Laplace, bar indicates the Laplace transform here. So u bar s is the Laplace transform of u. Similarly, f bar of s will be Laplace transform of f. All right. And now, this is nothing but the convolution, right? If I take the Laplace of this integral, it gives me the product of these two transforms, you see, from here. From here. If you take the Laplace transform of this integral, it is the product. It is the product of f and g. That's it. Right? So this is what I did. Because Laplace transform of the convolution is the product of the Laplace transforms of k and s, k and u. So I got that. Now I will not write s minus t or s minus u. No. Convolution gives Laplace transform at s. That's it. All right. And now from here, if I combine this us and us terms, I will get 1 from here and lambda k bar from here. All right. So 1 minus lambda k bar us is equal to f prime us. There is no us here. Of course, I took us as common. So this is just one us, not both. U bar of s and u bar of s. This u bar of s is not coming here. All right. So taking the inverse Laplace, because I'm not interested in u bar of s, I'm interested in u of s, u of x. All right. So this is the Laplace transform of u. So I need to take the inverse Laplace transform to get rid of this. So if I take the inverse Laplace transform, I'll get u of x back, and I'll be left with L inverse of this whole thing. And there is no ux again, remember. There is no ux. All right. So f bar of s divided by 1 minus lambda k bar of s. This us is not here. Everything is known on the right hand side. You can take the inverse transform. That will be your solution. So you see how easily I solve the integral equation with the help of Laplace and inverse Laplace transform. So let's solve these examples. I'll do one of them and you do one of them. All right, you do the other one. So let's do one of them. They are not difficult examples. I can pick any one of them and solve it here. And on the same steps, you can solve the other one. So this is of course a Volterra equation. All right, so we can solve it easily. All right, so this is your Volterra equation, given equation. This is the second example, second part of the example. You can do the first part on the same. First part had exponentials. Exponentials are considered a little easier, so I picked this one. Here, what the technique is, we just take the Laplace transform on both sides. Take Laplace transform of both sides. All right, so Laplace transform of ux is equal to Laplace transform of x. You can consider x as t now, right? And Laplace transform of this whole integral. And again, you have a difference kernel here. That's why you are not getting any problems taking the Laplace transform. Let's call Laplace transform again u bar of s. So this Laplace transform of x, it is t now. What was Laplace inverse of t? It was 1 over s to the power 1 plus 1. So it was 1 over s square. All right. Minus Laplace of this whole thing is the product of Laplace transform of. It is the product of Laplace transform of sine hyperbolic t and Laplace ut. Right. It's just the product. And now this has answer 1 over s square minus 1 square, and this is u bar of s. U bar of s. So what we can do is you can combine u bar s terms. So I'll get 1 from here and plus 1 over s square minus 1 from here. This is equal to 1 over s square. Now I will divide this on the other side. I will get u bar of s is equal to 1 over s square and 1 over 1 plus 1 over s square minus 1. All right, this is what we have. Now simplify the right hand side. If you take the LCM, you will get s square minus 1 on top. You'll get s square and s square minus 1 plus 1. So you got s4. S4 at the bottom. All right, so you can separate it. It's easy to simplify. It will become 1 over s square minus 1 over s4. All right, now it's done. I cannot simplify it any further. Now take inverse Laplace transform. Take inverse Laplace transform. We obtain Laplace inverse of us, u bar of s, is u of x, and Laplace inverse of 1 over s square minus Laplace inverse of 1 over s4. All right, so simply we are taking the Laplace. We took the Laplace transform. We isolated u bar of s on one side, send every other thing on the right side. Right side is known. Every function is known. I can take the Laplace inverse to get my ux back. This will be ux. And what is the Laplace transform of 1 over s square? It is t, I guess. T has Laplace 1 over s square, but our other variable is not t now, it's x. So x will come back. All right, and then minus s4. But s4 is not enough. If you have s4, you should have 3 factorial on top. Right? So you will multiply by 3 factorial and divide by 3 factorial. So now 1 by 3 factorial is outside. This is the Laplace transform of t cube, sorry, x cube. X is our variable, not t now. So x cube has transformed as 3 factorial by s4. So this is my answer. So answer is x minus x cube by 6. So see, I got the solution of the integral equation, this given integral equation. This was the given integral equation of Volterra type. And we used Laplace transform technique to solve it very easily. See how easy it was to solve integral equation with the help of Laplace transformation. So same way you can solve the other equation as well, right? It's again a difference kernel. You see it e to the x minus t. It's a difference kernel. So ux is equal to ex minus 0 to x e to the x minus t ut. Again, when you take the Laplace transform of ex is 1 over s minus a, s minus 1, minus this will again be, this is a convolution of ex and ut. So this will become the product of Laplace transform of e and Laplace transform of u. So Laplace transform of e is again 1 over s minus 1 times u. You will combine u bar and u bar, divide by the coefficient, you will get u bar of x in terms of s. Take the Laplace inverse transform to get your answer. So again, it's very easy, and the functions are not difficult, very well known functions. You know the Laplace transforms as well. So even you don't even need to find the Laplace transform separately. We remember them, all right, or consult the table to get the Laplace transform. So it was very easy. All right, so let's see the solution of an Integro-differential equation using a Laplace transform method, when the derivatives are involved and the integrals are also involved. Let's solve this one. That will be an interesting example. Integro-differential equation is an equation if both the operators differential as well as integral are present. Of course, by the name Integro-differential equation, it is very understood that both derivatives and integrals will be coming. For example, this thing. Solve the following integral differential equation subject to the initial conditions. And why we got the initial conditions? If you remember the formula, I will write it again. If you remember the formula from our last lecture when we were studying the Laplace transform of the derivative involves the value of the function at 0. That's why we need initial conditions. If we are not given initial conditions, we won't be able to solve it. All right? Similarly, you see this is another example of Integro-differential equation because we have derivatives on the left, we have integrals on the right side. All right? So we can easily find the solution of these integral equations. So I can solve again. There are two of them. I leave one for you and I solve one. This is easier one. So I can leave one for you. This is easier one because just one integration, one derivative, you can do it. Here, more terms are given, more integral terms are given. So maybe I solve this one, more complicated one, and you cope with this easier one. All right? All right, so this is your second example of Integro-differential equation. I left first one for you because it was simpler than this one. Here we have second derivative, first derivative. Similarly, on the right-hand side, we have derivative involved inside the integral and so on. So simple technique is exactly the same. Apply Laplace transform, solve for u bar, take the Laplace inverse transform. There are just 3 steps here. So I will take Laplace transform first. on both sides. So Laplace of u double prime minus 2 Laplace of u prime plus Laplace of u on the left hand side. Similarly, right hand side, Laplace of cosine x minus 2 times Laplace of 0 to x cosine x minus t u double prime t dt, and then minus 2 Laplace of 0 to x sine x minus t and u prime t dt. So this is what I got, right? Now, if you remember the formula, Laplace transform of second derivative was s square Laplace transform of u minus s Laplace minus s, the value of u at 0, and minus s to the power 0 and the value of u prime at 0. This was the Laplace transform of second derivative. Minus, we have 2u prime. So 2 times first derivative will have s with lu and minus the value of u at 0. This is the Laplace transform of first derivative. All right, and then we have plus lu, so that will be written like this. All right, right hand side, the Laplace transform of cosine is s over s square minus 1. All right, and then minus 2 Laplace transform of this is again a convolution of cosine and u double prime. So you will have a product minus 2 times product of Laplace transform of cosine x and ux, cosine x and u double prime of x. So again Laplace of u double prime of x. And this Laplace of u double prime of x is again s square lu minus su 0 minus u prime 0. All right, so again I can substitute. So this is 1 over, s over s square minus 1. And third term was, last term was convolution of sine and u prime. Convolution of sine and u prime. So this is minus 2. Convolution gives you the product. The product of sine x with u prime. All right. So again, this is s Laplace of u minus u0, and this is 1 over s square minus 1. So I can replace all the values. Now, what are our conditions? u0 is 0, u prime 0 is 0. u0 is 0, here u0 is 0, u prime is 0, u0 is 0. So at least our homogeneous condition make it little easier for you. So this becomes s square. What is Laplace of u? It is u bar of s minus 2s L of u. So 2s u bar of s plus u bar of s. This is plus u bar of s equal to s over s square minus 1 minus 2s over s square minus 1 times s square u bar of s. This is again s square u bar of s. Here minus 2 over s square minus 1 times s u bar of s. All right. So now if you combine all these u bar terms, this u bar term, this u bar term, all right, you will get u bar of s times, you need to combine all the terms, s square minus 2s plus 1, s square minus 2s plus 1, and then these two are coming from here, plus 2s cube over s square plus 1, plus 2s cube over s square minus 1, and here plus 1. I think sine and cosine has Laplace transforms plus 1, plus 1, plus 1. All right, these are all pluses. So plus 2s over s square plus 1. This whole thing is equal to what we are left with is only this term is left on the right hand side. So this is s over s square plus 1. This is what you got. So if you simplify, you will get this whole thing will be simplified to, so this whole, if you simplify it, this whole thing will be simplified to s square plus 1. That's how easy it will become. Because you see, here 2s over s square plus 1 is common. Inside you will get s square plus 1. So s square plus 1 will cancel out. You will get only 2s here. And 2s will cancel out. So you will get just s square plus 1. So just do it in 2 steps, you will get s square plus 1. So what you got is u of s times s square plus 1 equal to s over s square plus 1. All right. So now u bar of s is equal to s over s square plus 1 square. All right. And now we need inverse transform. And I know I don't know what is the inverse transform of that. So I need to do something. Either write it as a product. I think in one of the examples we have found the Laplace inverse of this thing. All right. So I can use the same example. So take the Laplace inverse now. Laplace inverse of us is equal to u bar of s is Laplace inverse of this whole thing. And if you recall, we have just solved this Laplace inverse in an example. And I mentioned over there as well as that if I multiply by 2a and divide by 2a, this is the derivative of the Laplace inverse of sine at. So you just multiply by t. All right. So u of x becomes not t. I am converting this to x, back to x, not to t. So that is 1 over 2a Laplace inverse of 2as over s square plus 1 square going to x. So that is 1 over 2a. So this is 1 over 2a Laplace inverse of, this is the derivative. This is the derivative of s over s square plus 1. As a is 1 here, so I just multiplied by 2. So if you take the derivative now, what is that? If you take the derivative of this thing, what you will get? You will get minus 1 over minus 2s over s square plus 1 square. So you see I can write minus 2 outside. So minus 2 is compensated now. Right? Now if you take the derivative, what will be the extra thing? Negative 1 by 2. So I replaced it by negative 1 by 2. All right? So now Laplace inverse of this thing is known. Minus 1 by 2 outside. What is the Laplace inverse of this thing? Laplace inverse of this thing should be, because the derivative has minus sign as well, I replaced it over there. And I think we should not write it here. I should write minus 1 to the power 1 and derivative first power. This was the formula basically. This was the formula that the inverse transform is the inverse transform of this, which is sine t, sine x, and x being multiplied. So this is, you got x sine x by 2. So that's your solution. Therefore, ux is equal to x sine x by 2 is the required solution. All right. So this is the required solution of the Integro-differential equation which I wrote at the beginning. So this is very easy. If it is complicated, becomes very easy, then the other differential equation, Integro-differential equation, will definitely be easier for you guys. So do practice with that example right now. Maybe just after watching this lecture, you should start solving the equations which I left off for you guys. This will really reinforce the topics which we learned, and you will not forget it later on. If you do it right now, you will not forget it later on. And definitely practice is the only thing which will help you in mathematics. All right? All right, so we solved this example very rigorously by taking the Laplace transform on both sides, using the properties of Laplace transform of the derivatives and Laplace transform of the convolution. We use these two properties to convert this equation to an algebraic equation basically. It became just an algebraic equation in u bar. We solved for u bar. We got u bar is equal to a function of s, and we took the Laplace inverse transform to get our ux back. All right? So there may be a little bit of trouble getting the Laplace inverse of the right-hand side, but in this case it became very easy. All right? So you should solve this other integral equation which is written here in green. Solve this integral equation. Again, on the left-hand side, you have to take the Laplace transform of the second derivative, which is s square u bar of s minus s u0 minus u prime 0. Again, here u0 is 0, but u bar 0 is 1. So you will get two terms on the left-hand side, s square u bar minus 1 equal to Laplace transform of e2x is 1 over s minus 2, and here it will become 1 over s minus 2 times Laplace transform of u bar, which is s u bar of s. Again, this becomes this will become the algebraic equation in u bar. Solve for u bar, meaning that keep u bar on one side and send everything else on the other side. You will get u bar as a function of s. Take the Laplace inverse transform, that will give you the answer. All right, so this technique is really very, very useful, not just for this integral equations or Integro-differential equations. Differential equation itself, if you are getting any differential equation, you can really easily solve with the help of Laplace transformation if the initial conditions are given to you. If initial conditions are not given, then of course that u0 and u prime 0, they will have no value. So you may see difficulties in solving that problem. So for initial value problem, it's really very easy to solve with the help of Laplace transformation. All right? So let's summarize what we did today. We started with inverse Laplace transform. It was very easy because we have already seen Laplace transform in the previous lecture. So it was easier to understand inverse Laplace transform. Then we went on to study the properties of inverse Laplace transform. And then we implemented this Laplace and inverse Laplace transform technique to solve the integral equations and Integro-differential equations. There were two examples for integral equation. I solved one of them. You should solve the other one right now. And solution of Integro-differential equation, again, two examples were written there. I solved one of them. I left one for you guys. So you should solve it right after the lecture so that you don't get this forgotten immediately. If you do it right now, I'm sure that this will be in your mind for hours. All right, so that is it for today's lecture. Thank you so much for being with me. I'll see you in the next lecture. Till then, Allah Hafiz and Assalamu Alaikum.